We now address the correlation aspect of regression and correlation. So if you recall, we looked at the points at industry scenario in the previous screencast, and we found the line of best fit was P equals this guy right here. We made a prediction with this equation about the profits in the year 2022, but then we thought, does it really fit it well? While this is the line of best fit, the line of best fit does not automatically imply that it fits the data well. That's the notion of correlation. So let's pretend this was the scenario we were in. The scatter plot was actually this with the profits, not what we originally had. It's these data here. You can see I've already generated this new scatter plot with this line right here. This line is actually the line of best fit. Would you say that this line fits this data well? Personally, I would say no. Even though this line is the line that minimizes the vertical distances between the points in the line, the points are all over the place. They don't lie anywhere near the line for the most part. And so in our actual example with the points at industries, the dots, while they didn't lie on the exact same line, they generally were close to the line. But how close is close enough? We need to generate the mathematical concept of correlation to be able to tell whether it is a good idea to actually use the regression equation to make predictions about the future. Let's first look at a qualitative approach to correlation. We'll get into quantifying it in the next screen. So notice here, if as the x values increase, if the y values decrease overall, notice they don't lie perfectly on the line, but they do lie near a line, this would be considered a negative linear correlation. If the same thing were to happen where the data falls along a line, but that line is increasing, then we consider that a positive linear correlation. Something like this has no linear correlation at all. There is no line that describes this data well. It's all over the place. And there is a pattern here with this data, but it's not linear. For example, this has a pattern that we could trace out that looks like what's called a parabola. So this would be like a quadratic relationship between x and y. So it's correlated, but not in a linear sense. This would be a nonlinear correlation. We want to focus on linear correlation. We quantify correlation with the notion of the correlation coefficient R. Sometimes you will see this written as capital R, but it's specifically either capital R or lowercase r. So we quantify the correlation in some way. So here are 6 examples. In this particular example, where you have the number of adult movie tickets versus the total cost in dollars, these points lie perfectly on a line. And notice the correlation is positive. We would consider this a perfect positive linear correlation because they all lie perfectly on a straight line. The correlation coefficient with that scenario is R equals 1. Let's look at the next scenario, checking out the relationship between height and shoe size. Well, roughly, as you get taller, you usually have a larger shoe size. So it's not perfect. It doesn't lie right on a line like this one does, but roughly it lies near a line, and in this case is increasing, so it would be positive. We would consider this such a relationship here a strong positive correlation, and it has a correlation coefficient of 0.81. In the next scenario, where we're looking at the relationship between income per year and the amount spent on milk, it has a roughly positive correlation, but it's not terribly good. If this is roughly what the line of best fit would be, the dots are pretty far away from it. So the correlation coefficient for this would still be positive, but it would only be about 0.45. In this particular slide here, they call this a weak positive correlation. We could call it like almost a moderate positive correlation. We'll discuss that in the next slide. But the coefficient here was 0.45. And then the next several examples, this has to do with negative correlation. This is a perfect negative correlation because it falls directly on the line. So that has a correlation coefficient of -1. This one is very strong, but not perfect. This has a correlation coefficient of -0.92. And this one right here is the most extreme. It doesn't have really any correlation whatsoever. This one, at least you could kind of tell that it's got an increasing feel to it. Here, there's no line would fit this very well. This correlation coefficient is R equals 0.04. And in that scenario, we would consider this to have no correlation. There's no relationship between IQ and height. So in general, your correlation coefficient R is always between 1 and -1. Now, to discuss how strong the correlation coefficient is, we can do a form of hypothesis testing, but we're going to avoid that and just use a table to represent general rule of thumb on how we should interpret the correlation coefficient R. You'll see that in the next slide. When interpreting the linear correlation coefficient, if it's -1, we consider that a perfect negative linear relationship. If it's around -0.7, we consider that a strong negative linear relationship. If it's around -0.5, we consider that a moderate negative linear relationship. -0.3, we consider that a weak negative linear relationship. And if it's 0, we consider that to have no linear relationship whatsoever. And then, of course, down here, you have the equivalent in the positive direction. So correlation coefficient R is always between -1 and 1, whereas the closer you are to -1 or 1, the stronger it is. In this case, at those extremes, it's a perfect linear relationship. And the closer you are to 0, the closer you are to having no linear relationship at all. On the previous screen, we had one of the examples had a correlation coefficient of 0.45. And while I don't disagree that you could possibly classify that as a weak correlation, which is what it was on the previous screen, however, we're going to use this table for doing our interpretations, and 0.45 is between 0.3 and 0.5, but it's closer to 0.5. So if you wanted to, you could call that a moderate relationship instead of a weak relationship. So what we're going to do, you're often not going to get an R value of exactly any one of these. We're going to see where our R values fall, and whichever thing is closest is what we're going to call it. So the 0.45 scenario, we're going to call that a moderate positive linear relationship. So let's get back to our points at industries example. Now, you may have noticed in the previous screencast, when we were looking at the line of best fit, there was also this R squared value. The R squared value for this particular set of data was 0.9444. Now that is not the correlation coefficient R, it's the square of it. And don't forget, you could see the correlation coefficient written as capital R instead of lowercase r. As you can see, Excel refers to it as capital R. So R squared equals 0.944 is technically the effect size of the relationship between the two variables. That's not something we cover in this class. However, we can get our correlation coefficient from that. So let's go over here. We've got that R squared equals 0.9444. How would you get R back from R squared? Well, the inverse operation of squaring would be square rooting. So we get R is equal to the square root of 0.9444. And you'll see why I left the gap here in a moment. So if you plug this into your calculator, you get approximately 0.97. Technically, there are two possible solutions to this equation right here. If you plugged in 0.97, you would get 0.9444. If you plugged in negative 0.97, when you square a negative, it becomes positive again, giving us 0.9444. So every number has two square roots, a positive and a negative. So when you plug this in your calculator, it's just going to give you this positive 0.97. You then have to decide, is your correlation coefficient positive or negative? And what determines that is whether the line is increasing or decreasing. If the line is increasing, you have a positive correlation coefficient. If it's decreasing, you have a negative correlation coefficient. So in this case, our correlation coefficient is positive. So we have R equals 0.97. Now, should we have used our regression equation to make this prediction in the first place, right? We used the equation to make a prediction about what the profits would be in 2022, but should we have even done it in the first place? Well, the correlation coefficient and your interpretation of that gives us the answer to this question. If R is 0.97, that falls really close to a perfect positive linear relationship. So it's not perfect positive, so I'm not going to say that it's perfect, but it's close to a perfect positive linear relationship. So since this relationship is so strong, it is absolutely appropriate for us to use this equation to make predictions. If this came out to be a weak positive linear relationship, then it would be a very bad idea to use the equation to make predictions about the future. So we need at least a moderate linear relationship, whether it be moderate, strong, or perfect, before we really should use this regression equation to make predictions about the future with this company. What if this was how the original data distributed? This is the slide you saw at the beginning of the screencast. Well, you can ask Excel to give you the equation of this line, and it certainly will do that. However, again, should we have used the regression line to represent the relationship between T and P if this was the data set? Well, for this data set, R squared is 0.0178. To get R, you would take that square root, you get square root of 0.0178, and we want the positive root because notice the line is increasing from left to right, and you get that this is approximately equal to 0.13. So we want to see where this falls. 0.13 is between 0 and 0.3, but it's closer to the 0. So it's closer to having a no linear relationship at all, but even if it was close to 0.3, that's a weak positive linear relationship. So let's classify this as a very weak positive linear relationship. Again, you could ask Excel to give you this equation of this line, and you could make predictions with that equation. However, it's a very bad idea because this is a very weak positive linear relationship between these two variables. So the correlation coefficient basically gives us permission whether we should proceed with the line of best fit equation or whether we should not do that. Also, the R squared value is not something you're ever going to compute by hand. We are strictly going to get this from Excel. We've completed our discussion of linear regression and correlation. The next 3 slides will show you precisely what you need to do in Excel to be able to get a scatter plot, get a regression line, a correlation coefficient, and to have Excel put the regression line in your scatter plot. First, of course, you need to open Excel and type your data into 2 consecutive columns. You need to highlight the data. Then click on the Insert tab at the top of the page. So you click on Insert, and you want to click on the graph that looks like a scatter plot, this one right here. Once you do that, choose the first one from the drop-down box. Then click on any of the dots in the chart. So you've got your data laid out. Click on one of these actual dots. It doesn't matter which one. Then you want to right-click and choose Add Trend Line. This screen will pop up over here. And you want to make sure that linear is highlighted. Display equation on chart. That gives you the regression equation. And display R squared. Make sure that's checked to give you the R squared value.